And lastly today, we've got two electromagnetic interactions that you need to be familiar with. And if you do AQA or Edexcel A levels, stick around for exchange particles right at the end. Right, so the first of these is annihilation, which you're probably quite familiar with by now. But when the first time you hear about it, it's very strange. So it's when you have a particle meeting its antiparticle and they disappear, their mass disappears. That's what annihilation is. And afterwards, you've just got the energy turned into photons. So it's always a 2-mark question on the exam. The first mark is for saying annihilation is when a particle meets its antiparticle, and the second mark is for saying that the mass of the particles is turned into energy. All right, but how much energy, you might ask, if you've got an electron and a positron, however much mass that is, how much energy are you going to get when you turn it into energy? And Q, the most famous equation in all of physics, it's that much energy. This is the formula. So many people know this formula, but obviously not nearly as many people actually know what it's telling us. It's the formula that allows us to convert between mass and energy. Now that we know you can, in fact, convert mass to energy and vice versa, this is the formula that tells us how much you're going to get. So here we've got the electron and the positron. So they've got the same mass because they're particle-antiparticle. So it's going to be this much mass times c squared is this much energy. So these photons between them have this much energy. Okay, and you can do this with other particle-antiparticle pairs as well. So, but then of course you're going to have different amounts of mass. So you've got a muon and an anti-muon, an up quark and an anti-up quark, or even a proton and an antiproton. It just has to be particle-antiparticle. And you're always going to get 2 photons given off. The more massive the particles are, the higher energy these gamma photons are going to be. And you're going to use that formula to work out how much energy they'll have. Right, and then the opposite of annihilation is also something that can happen. Again, it's an electromagnetic interaction, and it's called pair production, and it is sort of exactly the opposite. You start with, it's only 1 photon though, so you start with some energy in the form of a photon, and then that energy is converted to mass, and it makes a particle and an antiparticle pair. Now at this point we'll point out, why can't you just make an electron? Why couldn't this photon turn into just an electron? Have a little think. Okay, the answer is the conservation rules that we saw in the last video. We absolutely have to conserve charge, and this has 0 charge, so this side has to have 0 charge altogether. And this side we've got no leptons, and so on this side we've got to have no leptons overall as well. And so that ties us down. That's why it always has to be, oh, and sorry, baryon number as well, 0 and 0, that's fine. So that ties us down to a particle-antiparticle pair. And as we say, if you've got more energy available, you can make more massive particles. So you could make a strange and an anti-strange, for example. And if you had really, really high energies, you can make protons and antiprotons. Same applies, you just need a lot more energy to do that. Here's a question on annihilation. Okay, so the energy available, the total energy available is what we worked out just before there, using E equals mc squared, and then we're told that the 2 photons are identical, so they've got to have the same energy, so then we divide that by 2 to get the energy of one of the photons, and then we use E equals hc over lambda to get the wavelength of the photon there. Okay, if you do OCR A-level physics, you can switch off now. Everyone else, time for exchange particles, which are sometimes called force carriers. I'm not very happy with this name force carrier because I don't like the idea that you're passing a force around, but never mind anyway. The point is that we've got non-contact forces here. And if 2 things aren't touching each other, how are we meant to understand how they're interacting? And so this model has been, someone has come up with it, which helps us to think about how it works, and in fact it sort of turned out to have a lot in it. Okay, so we're going to imagine two people on skateboards, and one of them is going to throw a really heavy ball towards the other, and they're going to catch it. So when this person throws the ball that way, they're going to move the other way. So this is Newton's third law, just like our Newton's third law video. So they're going to move that way. And then when this person catches the ball, they're going to move that way. So this is a model for how you could have two particles repelling each other by exchanging a third particle. And this third particle is called the exchange particle. So that's what we're doing here. Okay, but this was repulsion. What about attraction? Well, you're going to love this. This time we're not passing a big heavy medicine ball, we're throwing a boomerang. So the person throws the boomerang, and then when the other person catches it, they are pushed towards the first. This person, throws the boomerang that way, which makes them move this way. The boomerang turns around all the way back here, comes back, gets caught by this person, and they move this way. And so this is that's a model for attraction. These are quite fun ways to think about what we're saying is happening with the physics. And so once again, the boomerang there is the exchange particle for the force. Right, we draw interactions to represent the exchange particles using Feynman diagrams. And in a Feynman diagram, we've got time moving that way. So let's do, first of all, say we're going to do an electromagnetic interaction first. So we're going to have two electrons that are repelling each other. So we draw arrows to show that these are the two particles that we have beforehand. So they're coming in as time goes forward. And then one of them is going to release the exchange particle. It's going to like throw out the ball, and the other one's going to catch it. So when this one throws the ball out, it gets pushed off in the other direction, and when this one catches the particle, it gets pushed off in the other direction. So this is, and afterwards there's an electron going the other way and another electron going the other way. So it's the same particles as before, they've just repelled each other. Now the name of the exchange particle for an electromagnetic interaction is a virtual photon. A virtual photon. Now, it's obviously quite a complicated idea, this, and so they don't expect you to have a huge working knowledge of this. All they really want you to know is that if it's an electromagnetic interaction, then the exchange particle is a virtual photon, and if it's a weak interaction, then it's either a W plus boson, it's called, or a W minus boson, depending on what charge it needs to have to fulfill charge conservation rules. And so here is an example of a weak interaction, and you're going to use your conservation laws to work out what particle Y is and then which boson it needs to be, W plus or W minus, for the exchange particle there. Okay, so we have got coming into this interaction a proton, and then coming out of it a neutron, a positron, and something else. So here there's our proton, and it's going to turn into a neutron plus a positron plus one charge and something else. Now we're going to do our conservation rules. So we've got the charge, total charge before the interaction is 1 plus 1. And then total after, we've got 0, 1 there, so this is going to have to be a 0. And then baryon number, that's the top one. We've got 1 beforehand, and that's 1, so this is also going to have to be 0. And then lepton number, this is made of quarks, no leptons here. also made of quarks, no leptons. I'm going to write this one out. So we've got no leptons before, and then that's got no leptons in it. Now, but this is a positron, so that is an anti-lepton. So I'm going to put -1 there. And so that means that this must be +1 lepton. So this needs to be it needs to be a lepton, not an anti-lepton. And it's got 0, 0. So 0, 0 tells us it's a lepton 0, 0. That means it's a neutrino. And electron neutrino to match. Now, is it a neutrino or an anti-neutrino? It's a neutrino because it's not an anti-lepton, it's a lepton. Right, so we have got that it's going to have to be an electron neutrino, so that's either this one or this one. And then if we look at charge conservation on this moment here, the proton has +1 charge and the neutron has 0 charge. So you've got +1 coming in and you must have +1 coming out. So that means that this particle here needs to have +1 charge. So +1 coming in and in total +1 coming out. And so that means that it is a W+ boson, and A is the right answer there.